Bleeker again, lesson 7.2, multiplying polynomials by monomials. So the big idea is that once the lesson's done, you should be able to multiply these and have a new expression. And it's been a lot of formula work, so let's get going. We got a lot to do. If you remember, we had a few species down here we had to define. These little guys here, these little tiles, those are called constants, and we know their value. Each one is worth 1. Now we have to keep an eye on whether they're positive or negative, but they represent real counting numbers, okay? When we look at some of our unknowns, we have our rectangles, which will represent the value of x. And again, just a little bit of review here. If we set up a couple of those rectangles vertically and horizontally, as in 2, we would have a squared term because their sides would be the same. So we say this is an x squared term. Over yonder, on this side, what we have are the negative counterparts. So we have the -1 constant. We have the negative x. So let's label those. We'll use a different color. And this is negative x squared. So we'll give it a lighter color. So applying the rules that we should be familiar with by now, really this is a game of multiplying the coefficients. Now the coefficient is that number which is out in front of your variable. And you're multiplying your coefficients, you're multiplying your variables, and you're multiplying your constants, however this may come up. So we're going to continue to use what's known as the area model, where we multiply length and width. We'll come down to example 1 below here, and we'll get right on this. Okay, so zooming in. Now in this case, what we've got on one side is we've got 5 units of length and a little bit more that we're going to refer to as 3x. So the side we're looking at is here. We say that this side's length will be represented by 3x plus 5 units. The width itself will be represented by 4x. So a neat little trick is just to identify what you're looking at for length and width. So this would be the equivalent of our width, and this would be our length. So we've got our expressions in place. That's why the area model is really handy. We're going to be multiplying a monomial, which is here, by this term up here, which is essentially our polynomial. So what do you get? Well, when you multiply 4x, and I'll use parentheses for the multiplication, multiply it by 3x plus 5, you use, let's just switch colors, you use something called the distributive rule. The distributive rule states that the first term has to be distributed or multiplied by each of the second terms. So that's why I'm drawing these little jump arrows, to make that really obvious. Alright, choose a different color now. Let's go with, say, purple. Your answer is going to be 4 times 3, which is 12, and x times x, applying our exponent rules, 12x squared. Now when we go to our second procedure, remember that it's 4 times positive 5. It's important. I always sort of put a circle around that so that you know what you have is a positive 20 value. And that, ladies and gentlemen, is our finalized expression. I'm going to go back to yellow. And there's our answer right there. So the area of a rectangle with width 4x and length 3x plus 5 is 12x squared plus 20. Interesting. Take a moment and see if you can apply that same example. Hit pause and see if you can figure out the next one. Now, just because we've turned this rectangle up on its end doesn't mean that I'm not going to give you the hint by putting in plus there because these go together, right? And this is an expression where those little brackets there might have given it away. You hit pause. I'll be back as soon as you click start. Okay, so the expression that we have in this case, you can say whichever side you want is length or width. It really doesn't matter. Let's call this the length, and we can call this the width. So if area equals length times width, if that's our simple formula, then you just use the expression that you have for length, and you have an expression for width. So our answer is going to be 5 meters multiplied by 2.1. Now this time I've actually put the multiplication sign in between. 2.1 m. Did I say meters? 2.1 5m multiplied by 2.1 m plus 7. There we go. So again, what we need to do is call up our distributive rule. Hate it when I do that. Change the color, this little pen tool, and it if you don't hit done, it changes it all. That's all right. 5m multiplied by 2.1m gives us 10.5m squared. And the next one that we would do is 5m multiplied by 7. 5 times 7 is 35, and there's an m along for the ride. This is positive because the coefficient 5 multiplied by a positive value of 7 stays positive. So that's your expression. So we could fill in this whole thing now and say that this is the expression for our area. So what have we got? We've got a rule that's popped up which states that when multiplying a monomial by a polynomial, you multiply the monomial by, wait for it, here it comes, all the terms in the poly. I'll say poly for short, but of course I mean polynomial. So we call that the distribution rule. You have to distribute the monomial to everybody in the polynomial. And that is a very important rule. It's essentially just a multiplication rule that you need to see everybody get multiplied. The two terms, the monomial and the polynomial, there has to be a distribution, and that's what these arrows up here represent. That 5m had to be multiplied by both of the terms, distribution. Now once you see this, and once you get the hook of this, or the hang of this, I haven't had enough coffee, what you see, it is a game of multiplying coefficients, applying the exponent rules for variables, and multiplying with constants. Now you can use the area model to do this, so we will. I have to zoom in a little more. Right? And the area model would say, let's say you have 3 x's. Do my best to fit them all in. There we go. They're positive, so we'll colorize them. And you've got 2 of these x's. So our 3x is accounted for here. And here's our 2x. Again, they're positive. And then minus 1, which is just like that. So if we just put in our length and width bars like that, there we go. Then based on our shapes, we've got, doing my best here, but it is freehand, looks like we've got 6 squares popping out of there. Now because we have positive value times positive value, these of course I'll fill in because they're positive too. So they're all x squareds. And we're left with this little devil, this this white one here changes the color of our ensuing rectangles here. There's one of each of these rectangles, but they'll all be negatively charged, so to speak. So I'll hit done. I'm going to come back with what shows up well on purple. How about green? So our answer, when you multiply 3x's by 2x's minus 1, is that you get, again, let's hit done. Choose a slightly different color. I'll go with, let's go with orange. You get all these x squareds. In fact, there are 6 of them. And these negative x's. Now you just use a process of collection, and you say, well, how many do you have? Go back to blue. You have 6x squareds minus 3x. And there you go. That is your final answer. Now I'll let you take a stab at B. Obviously, it's the same example as above. See how you do. For the sake of brevity, I'm just going to move on to the next example. I'm also kind of out of space. Can you recognize? Actually, just before I go on, pause it. See what your final answer is. I will do this sort of the old traditional way. I'll tell you what the answer to this is right now. So if I do the distributive rule, and I use the arrow trick, okay, hit pause, don't cheat, do that with the area model. If you're back, here's the answer. 3d times 4d is 12d squared plus 9d. Okay, so if you'd set this up, there probably isn't a lot of space here. You should have counted 12 of those squares, right? They should have been filled in, and 9 of the little rectangles is what you would have gotten. All positive. Now, not meaning to bounce around, what multiplication statement do you see here? Well, you have to identify what your sides are. So let's say that we identify our length and our width. So what we have is x being multiplied by 2x squareds plus 3. And since they're darkened in, we'll say they're all positive. The answer in the middle, right here, is our product, of course. What does this mean? It means that we get, oops, make sure that I identify these as being 2x's, not x squared. So I'll just correct that little oversight there. X multiplied by 2x plus 3. Sometimes you jump to your answer in your question. X multiplied by 2x plus 3. You get 2x squareds and 3x's. 2x squareds plus 3x's. There we go. Looking at the other side, let's go to scroll here. Same story. We identify our players, and we say that we have negative x's here, positive x values there. These are each minus 1. And we have 3 of them. So what we get is what we expected, some negative x squareds. And because these values are white and these values are white, negative times a negative equals a positive. So instead of white rectangles, we get positive ones, dark ones. And we can collect our like terms and say our answer is negative 4x squared plus 6x. So you'll be expected to be able to do that. That's part of the course. This turns out to be really useful. You could do this all day long when multiplying even really large polynomials. This area model comes in very, very handy. Okay, so in example 4, you've got several, it's saying use models to expand each expression. I'm going to do B. I'll do the one in the middle just for the sake of space. Go like that. So negative x multiplied by a positive x, and then 4. 1, 2, 3, 4. Let's color all these in. And then I'll even include the variables as well, because I think it helps you to see it. Here's your negative x. Here's your positive x. 1, 2, 3, and 4. So again, you get an x squared out of this, but since this is negative, you get a negative x squared there. It should be white. And here you get one of everything that these little guys are being multiplied by, but it turns out that since this is negative and you're multiplying by positive values, that negatives reverse the signs of positive values. So these are all negative. So our final answer, just wall this off, is negative x squared minus 4x. In case you're wondering what the coefficient is there, you've got one of those negative x squares. So it just proves that you don't always have to write the coefficient minus 1. Okay. So what have you got? You've got this distributive property. And I like to say it's where the monomial gets multiplied by everybody. That's my way of understanding it. I've always understood it that way. It works really well. Now let's put it as correctly as possible. Distributive property, in the case of this lesson, is the multiplication of the monomial by each term of the polynomial. Okay, and let's write polynomial. There we go. And then we'll highlight, because we can do that. I like doing this on an iPad. It works out really well. I got a little Target stylus here, and multiplication of the monomial by each term of the polynomial. And that's it. That's as hard as it needs to be. Move this up a little bit, and just using our arrows, you can show those two multiplication steps and just look at the values and make sure that whether what you have is positive or negative. So 5m times 2m is 10m squared. Everything was positive, so it stays this way. And 5 times 3 is 15, and m is along for the ride, still multiplied in. There you go. You're going to have to be able to undo that, by the way. When you look at your answer here, you can see a factor that could be divided out. You sort of know this is coming in the future, don't you? Where you can slim down a polynomial to its well, take out its factor, which is 5m. But that is coming, so we'll reserve that for the future. Just know that if I multiply the 5m through with distribution, I can take it back out again using division. And you've got a plethora of examples here. So I'll hit a few. Negative n squared minus n. And that minus sign reversed the signs of what it was distributed against. You could also go like this, save yourself a little bit of room. 2.6x squared, and 13 times 5. Here's a little trick. 13 times 5 is 65. there's one item behind the decimal place in 1.3x. So put one item behind the decimal place in your answer. Sneaky. Minus 6.5x. Doesn't matter what order you multiply in. You can multiply forward and backwards. So I like to multiply the monomial through. So I'll just go in the opposite direction. This time I'll go to the right. Negative 3m squared plus 6m. Now, I'm going to show you something neat here and just stop and make this point. As long as you have the value of the coefficient, positive or negative, correct, you can reorder this thing. You'd better keep the coefficient positive or negative. Now, normally you wouldn't do it this way, but this is the same as 6m, which is positive, understood, minus 3m squared. As long as we have the signs correct, we can rearrange the values in the expression, but you've got to keep the signs correct. What do we got here? One more quick one. Negative 12.3k, and in this case you've got to keep your eye on that minus value there because it cancels out with your negative value here for your coefficient in front of k. So this looks like it is positive 15.9. Needed to put a squared over there, k. So there we go. You have to watch your exponent rules. Sometimes you'll be hustling your way through an example and you think, oh yeah, I got the coefficient right. You're so focused on the coefficient that you forgot the exponent. Look at your answer when you're done. Take a second look at it and be sure that what you expected to be there is there. Right? It's called being thorough. And there's some more examples for you to try here, but they're just like what you saw above. Just watch and be very careful because this is positive and this is negative. And that's really important. I go right after it as soon as I do these questions. Negative 8x squared plus 12x. And I knew the sign on that was changing because the negative 4 coefficient and the negative value of 3 were going to collide and it was going to become a positive result. Okay, so there's a great number of these to move through. You can have a fractional coefficient. 2/3 of 9 is 6. That's a good one to know. And if you can't remember that, 2/3 times 9, understood to be over 1, is the same as 18 over 3, which is 6. Although if you've been paying attention to your cross-canceling, which you should know, you can cross out the greatest common factor of 3 and 9. You can divide that out, essentially, and you're left with 6, nice and reduced. Our answer is negative 6m squared minus 36m. Watch your signs. It's pretty important. Okay? Since I've gone and done a fractional version of d, I'll let you go ahead and do the fractional version of this. Remember to place these over 1 if that's what you need to do. Right? It'll help you do your multiplication and any canceling a bit more accurately. Okay, so for our last example, we'll go over just a word problem which exemplifies what we've been doing all along, which is multiplying monomials by polynomials. Now, the one thing I notice in some word problems is in order to make them a little bit more understandable, not enough students draw. Watch what the first thing is that I pretty well do here. They talk about a cement pad, and I get the idea. Okay, so we're talking about a rectangle. And they've given you some information right here. They say the width is 5x and the length is 3 longer than the width. So you sort of have to stop and think and you say, Well, what's the width and what's the length? Well, the width is given to you. Now, let's be clear, this is 5 meters. Okay, and let's write in meters over there. They're not using m as a variable, they're using it literally as in meters. So the expression for width, let's call this width, is 5x. And the length is the same as the width. So there's the same. And it's a little bit more, 3 meters longer. So let's grab the highlighter there. Width is 5x, and length 3 meters longer than 5x. So we've got our expression. Let's see what we can do with following up with it. Again, it's just length times width. So I meant to grab a different color. Let's go back to orange. We have 5x representing one side being multiplied by the other side, which was just 3 more, like that. So we've got the distributive rule that we need to take care of here. So first multiplication and second multiplication. Good for your answer, which should be 5 times 5 is 25, x squared plus 15x. Okay, so there we go. If they came along and told you that x was 2 meters, you'd probably be a little bit annoyed. You'd say, well, why couldn't you have told that to me sooner? Well, if this was a formula and you got the information later, well then at that point you'd be able to just plug it into a simplified expression. Here, we can do this 2 ways. It's actually a good instance to see, did this or will this work out? 5x is like 5 times 2, and 5, now that x is known to be 2, we can do a little bit of math and say, well, that 5 times 2, that side is 10, and that side is 13, which is good for 130 meters squared. Pretty big pad. Question is, does this work? Now that we've applied the distributive rule, if I bring that down, do we get the same answer? It should be the same value if our math holds true. 25 times 2 squared plus 15 times 2, now that we know that x is equal to 2. 25 times 4 plus 30. Oh, we can see where this is going. This is 100. This is 30. 130 meters squared. Well, look at that. It worked out as we expected it to. The reason why, folks, is that the distributive rule is just multiplication. And that's what we were doing on the left. And by applying the distributive rule, we've shown that by distributing that 5x through that monomial through the polynomial, that we just have the exact same value. It's just expressed in a slightly different way. Sure, it was 5x wide by 5x plus 3 long, but if you multiply that out, another way of saying that is the area of this whole rectangle right here, if you actually do the length times width, is this value. It's another way of saying it. Mathematically, it's totally dead on. Okay, folks, if we scroll down, you can see your assignment sitting at the bottom. So have a good one, and have fun shoveling the snow, because there's a heck of a lot of it falling these days. Hasta luego.